The butterfly effect is one of the most striking concepts that sparked many of us to take an interest in science and science fiction. Let's be clear right from the start. A recent study suggests that the butterfly effect may not be as powerful as we once thought. In fact, it might not even exist at the quantum level. What's more, this claim is backed by strong arguments and experimental evidence. The study in question was conducted by theoretical physicists Bin Yin and Nikolai Sinitsyn from the Los Alamos National Laboratory, which operates under the U.S. Department of Energy. In the research, a physically simulated time travel scenario was used to test whether an intervention made in the past at the quantum level would have any effect on the present. The results of the study were published in the prestigious scientific journal Physical Review Letters and directly sought to answer the question: does the butterfly effect exist in the quantum world? The butterfly effect is one of the core concepts of chaos theory. It argues that a small change in the initial state of a system can lead to large and unpredictable consequences over time. For example, according to one claim, an event that seems completely unrelated, like a bat transmitting a virus to a mouse, can end up forcing the entire world to stay indoors for 2 years. This is exactly what we experienced during the pandemic. We first encountered this concept, especially in weather forecasting. Over time, it became a frequently discussed idea among those interested in chaos theory. Although the idea dates back quite far, the person who popularized the concept of the butterfly effect was the American meteorologist Edward Lorenz, who worked in the 1960s. While working on weather simulations, Lorenz discovered that making a very small change in the initial data, such as entering 0.50 instead of 0.51, completely altered the outcome of the calculations. This observation revealed that even deterministic systems, those governed by the rules of classical physics, can be entirely unpredictable in the long run. Just like the three-body problem, even if the rules of the system are known, you still can't predict with certainty what will happen over time. But a recent physical experiment is now challenging this perspective. Returning to the study published in Physical Review Letters and conducted at Los Alamos National Laboratory, famously known as the place where the atomic bomb was developed, we see that at the quantum level, things are neither as Lorenz suggested, nor as Heraclitus of Ephesus claimed in ancient Greece. Heraclitus believed that the order of the universe was intertwined with chaos, and that every kind of order contained a hidden chaotic structure. But the quantum world seems to reject this classical action-reaction confusion. In fact, if it weren't for another theoretical study conducted not long ago, this new experimental argument might not have stood on such solid ground and probably wouldn't have gained much attention in the scientific literature. But now we know this. For all quantum processes, no matter which direction the arrow of time points, whether forward or backward, quantum calculations produce consistent results. In Markov processes, which are used to calculate how a quantum system evolves over time, the direction of time has no mathematical significance. No matter which way you look at it, the outcomes are perfectly consistent with Schrödinger equations. That is, if you reverse the arrow of time and calculate an energy level and get the value x, you will still reach x when calculating the same system forward in time. It's like watching a movie from beginning to end or from end to beginning. The sequence of events might change, but the ending remains the same. And at this point, a striking truth emerges. Even when the direction of time is reversed, quantum correlations remain intact, and no information is lost. And if information is preserved, the system can return to its original state, even if it is disturbed. In other words, the butterfly effect may not be real in the quantum world. At least, that's what this experiment seems to suggest. Thus, unlike classical physics, it becomes possible to run simulations both forward and backward in time within quantum systems, whether you have a quantum computer or a very powerful classical one. As long as you know the rules by which the system evolves, you can simulate quantum processes in both directions of time. And that is exactly what the scientists at Los Alamos did. Using a quantum computer, the researchers simulated the flow of information over time and tested whether a true butterfly effect exists in the quantum universe. The experimental setup might seem simple, but the idea behind it is incredibly deep. Think of it this way. Inside the computer, there's a qubit. That qubit represents a piece of information. For example, imagine you flipped a coin and it landed on heads. The researchers took that piece of information and loaded it into a central qubit. Then, They made that information interact with other qubits in the same system. During this process, the information became deeply entangled and mixed with all the other qubits, like a drop of ink dissolving into water. In quantum computing, this stage is called scrambling. Scrambling means taking information from a single point and spreading it across the entire system. At this point, the information is no longer stored in one place. It's now embedded throughout the group, in every corner of the system. And so, we would expect that if you damage just one part of the system, that damage should theoretically affect the whole thing. But interestingly, that's not what happens. The experiment was carried out on IBM's 5-qubit quantum processor. In the system they used, 3 qubits were active, 1 served as the central qubit, 2 others acted as a bath or mixing environment, and 1 was used as an ancilla or helper qubit. At the end of the scrambling phase, the information in the central qubit had been spread throughout the system. Then, the direction of time was reversed, and the system evolved backward. But this reversal was not physical, it was mathematical. In other words, the inverse of each operation was applied step by step. In quantum systems, such reverse transformations are made possible using the inverses of unitary operators. Now we come to the truly fascinating part. While the system is fully scrambled, meaning the information has been spread across all the qubits and time is flowing forward, the researchers intervene with the original central qubit. A measurement is made on a random axis, which disturbs the quantum state of the qubit. This creates a small change in the system, but that tiny intervention could, in theory, lead to massive consequences. Much like the idea that a butterfly flapping its wings in the Amazon could trigger a hurricane thousands of kilometers away. So what do they do next? They rewind time. In other words, they mathematically reverse the evolution of the system. Why would they do this? Let's make it more concrete. Imagine we have a quantum system that evolves from time t to time t plus 1 and reaches a specific energy level. But then at time t plus 1, a small disturbance, a potential butterfly effect, is introduced. Afterwards, the same system is reversed back in time to t, but now it carries the effect of that tiny disturbance with it as it moves backward. If the butterfly effect held true at the quantum level, the system should look drastically different when it returns to time t, perhaps with its energy level multiplied by 10. But that's not what happens. This leads us to an important question. What does it mean to reverse time at the quantum level? Are we really going back to the past? Of course, there's no physical time travel happening. But thanks to quantum computers, operations at the particle level can be reversed. Because quantum operations, when defined mathematically, are reversible by nature. That means if you apply the same operations in reverse order with the same precision, the system can theoretically return to its original state. And that's exactly what the researchers did. After reversing the system, they looked again at the central qubit. If the system were truly sensitive to the butterfly effect, that small disturbance should have grown and changed everything. But it didn't. You don't need to physically reverse each step to rewind the system. Instead, a quantum operation is applied that mathematically reverses each action. In quantum mechanics, this is called the inverse of a unitary transformation, the conjugate transpose. Since quantum operations are inherently reversible, quantum computers can perform such transformations with great precision. It's important to note here, this is not real-time travel, but it does mean that the system is mathematically returned to its past state. And here comes the surprise. Against expectations, the final state of the system turns out to be almost identical to its initial state. In the final measurements of the experiment, the original state of the central qubit was recovered with over 98% accuracy. In other words, the intervention made in the past did not grow into a disaster as it would in classical physical systems. Instead, it was suppressed, even corrected, within the quantum evolution. This is truly a remarkable discovery. Because in classical physics, and according to our intuition, chaos destroys information. For example, when you burn a book, the information is gone forever. But in the quantum world, information is never completely lost. It only becomes dispersed throughout the universe. And this experiment goes one step further by showing that in the quantum world, the butterfly effect doesn't work the same way it does in the classical world. What's more, this experiment not only redefines the limits of the butterfly effect, but also shakes our understanding of time travel. Some recent discoveries at the quantum level suggest that time can, in theory, be reversed, implying that time travel may be physically possible. Yet these results also suggest that a small change made in the past may not always affect the future. So yes, time travel might be possible, but going back to change the past, at least in the quantum world, doesn't seem to be very effective. If you like our videos and subscribe to our channel, we can reach even more people. See you in the next video. Take care.